Mr. Frappier.
Okay, then good afternoon, Mr. President, members of the Commission. For the record, my name is Jerry Frappier. I'm the Director General of the Directorate of Power Reactor Regulations. I'd like to thank you for the opportunity to present the risk-informed assessment of CANDU safety issues as a technical briefing. With me today are Dr. David Newland, Director General of the Directorate of Assessment and Analysis, and Dr. Doug Miller, Lead Technical Advisor for the Directorate of Major Project Management and Regulatory Improvements. We also have numerous technical personnel that are available to provide details. And as you mentioned, the licensees are here, including New Brunswick Power, who you mentioned OPG and Bruce, but New Brunswick Power is also here.
Sorry about that.
And so today's presentation will provide some background on the CANDU safety issues, discuss a bit how we did the categorization since last we spoke to the Commission on these items, our approach to managing the CANDU safety issues, the current status of them, and then some conclusions. Uh-oh. Yeah, thanks, Doug. There we go. Before we get into the details, I would like to provide some context, however. This presentation will provide some details on some very, very technical subject matters, which can lead to, which I'm concerned might lead to some confusion with respect to the current status of our operating plants, our operating reactors. So I'd just like to start off by being very clear. The nuclear reactors operating in Canada meet all the regulatory requirements, and licensees are qualified and are making adequate provisions to operate the reactors. The safety cases for currently operating reactors fully apply the defense in depth framework and have appropriately conservative safety margins. However, in the nuclear business, that's never quite enough. We're always looking for more. And so as a healthy safety culture of nuclear regulators includes having a questioning attitude, looking for opportunities to continuously improve safety and increase regulatory knowledge. And it's within that context that these issues are being talked about today. Ongoing regulatory research, peer reviews from international experts, and taking operating experience into account are key aspects of continuous safety improvements and increasing our regulatory knowledge for problems today, but more importantly for problems that might come tomorrow. So the risk-informed assessment of CANDU safety issues focuses on the activities undertaken to confirm the adequacy of safety margins, increase regulatory knowledge, enhancing the safety of CANDU reactors. And with that, I'll turn it over to Dr. Doug Miller, who will continue on with the presentation.
Doug Miller, for the record. Regulatory decisions are based on the best available science. But a regulator needs to have a questioning attitude, seeking continuous safety improvement and increasing regulatory knowledge. As such, one element in the framework of the International Atomic Energy Agency activities is to assist member states in reassessing the safety of operating nuclear power plants. In collaboration with the International Atomic Energy Agency, regulators of countries operating each type of reactors initiated work to enhance regulatory effectiveness through the exchange of safety-related information. This initiative resulted in the identification of generic safety issues for several reactor types. The compilations were published as technical documents, or Tech Docs as they're called, and include Tech Doc 640, safety issues for the Russian design reactors WWER 440, which was published in 1992, Tech Doc 1044, generic safety issues for light water reactors, that includes both pressurized and boiling water reactors, and was published in 1988. And finally, Tech Doc 1554, generic safety issues for pressurized heavy water reactors, or CANDU type reactors, and was published in 2007. These represented, at the time, a compilation of what was defined as safety issues for these three types of reactors. There is information in the CMD indicating the list of items identified by experts with operating experience for each reactor type. It is through initiatives such as this that the best available science is used, but also at the same time challenged. In 2007, CNSC staff were the main contributors in the development of the International Atomic Energy Agency's technical document on generic safety issues for nuclear power plants with pressurized heavy water reactors. We also developed an initial list of technical issues using this document and consolidated the safety issues in this with the CNSC's generic action items that existed at the time, which included findings from ongoing nuclear safety research and experience feedback from regulatory oversight of currently operating CANDU reactors in Canada and worldwide. Collectively, these technical issues were referred to as the CANDU safety issues, or sometimes we call them CSIs. The CANDU safety issues topics include the adequacy of computer codes, safety analysis methodologies, aging of systems, structures, and components, fire protection, seismic design, functions of pumps and valves, electrical system performance, instrumentation and control system performance, containment, auxiliary systems such as service air, service water, and instrument air, fuel behavior, and reactor core behavior. So it really did focus on the areas that we refer to as safety analysis, plant design, and fitness for service, collectively those three safety and control areas. So as discussed, ongoing regulatory research and taking operating experience into account are key aspects of continuous safety improvements and increasing regulatory knowledge. We have reported on these initiatives in regulatory oversight reports and during license renewals. However, this CMD consolidates the CNSC staff reviews. This CMD will describe the risk-informed decision-making process followed to develop the path forward for resolution of the CANDU safety issues. In 2007, an expert team of CNSC staff followed an expert elicitation process to assess the CANDU safety issues as follows. CNSC experts considered whether the item was addressed in initial licensing of the facility, whether safety analysis methodologies were appropriate, or design upgrades have been made since initial licensing. The CANDU safety issue, the item that you see in the report, was determined not to be an issue in Canada if this was the case. These are referred to as Category 1 CANDU safety issues. Next, we considered whether existing measures in place by licensees need additional confirmation or improved knowledge or understanding was needed to reconfirm the adequacy of safety margins. If the answer was no, it was determined that the licensees have appropriate control measures in place to address the issue and to continue to maintain safety margins. The CNSC, through their regulatory oversight, continues to monitor licensees' management and continued progress towards resolution of the issue or management of the issue. These were referred to as Category 2 safety issues. Category 2 CANDU safety issues can be those subject to ongoing regulatory oversight, such as component lifecycle management programs that involve component inspections and review of inspection results by CNSC staff. In addition, they can be those subject to an ongoing review, such as the results from an analysis methodology. An issue was categorized as a Category 3 CANDU safety issue if further experiments, research, and/or analysis are required to improve knowledge and understanding of the issue or to confirm the adequacy of the safety margins. In this case, the CNSC's risk-informed decision-making process was applied to develop the path forward, or as we say, the risk control measure for issue resolution. The CNSC reconfirms the adequacy of safety margins and monitors licensees' management of the issue to ensure its timely and effective resolution. So, to summarize, Category 1 is not an issue in Canada. There is minimal regulatory oversight unless there is a change regarding the item, that there's a discovery or OPEX worldwide that would make you challenge some thinking. But that's been very rare. Category 2, the issue is a potential concern in Canada. However, the licensees have appropriate control measures in place to address the issue and to maintain safety margins. The CNSC continues to monitor licensees' management and progress towards the issue. For Category 3, the issue is a concern in Canada. However, the licensees have control measures in place to maintain safety margins but further experiments and/or analysis are required to improve knowledge and understanding of the issue and to reconfirm the adequacy of safety margins. The CNSC evaluates the reconfirmation of safety margins and continues to monitor licensees' management of the issue to ensure its timely and effective resolution. Essentially, Category 3 items require more focused regulatory oversight. An example of a Category 1 CANDU safety issue is as follows. One of them was systematic internal flooding assessment, including backflow through floor drains. So if there is an inadvertent spill, could a backflow impact on safety systems? Direct flooding from liquid releases as well as backflow flooding of safety systems through drains is a potential problem with implications that are broad in nature. In Canada, a systematic assessment of internal flooding is a licensing prerequisite. It had to be done from day one. For example, calculation for reactor building flooding was done to show that the flooding sources in the reactor building do not affect safety functions needed to control the reactor. An example of a Category 2 is steam generator tube integrity. Concerns relating to the steam generator tube integrity stem from the fact that the steam generator tubing is subject to a variety of degradation mechanisms. These degradation mechanisms can impair tube integrity if they are not managed effectively. As part of safe operation, Canadian utilities are required to develop and implement steam generator tube integrity programs. The tubes are inspected according to the periodic inspection program as per the requirements and acceptance criteria in CSA standards. In addition, in-service inspection plans are developed to manage the ongoing in-service degradation discovered during inspections. The CNSC reviews inspection results, but we also look at the adequacy of the plans in view of the inspection results and looking forward, taking OPEX into account, where to focus efforts on any novel or unexpected steam generator tube degradation issues. We will provide more specific details on the status of Category 3 CANDU safety issues in just a couple of minutes. In 2007, when we did the initial assessment, there were 24 Category 1 issues, 29 Category 2 issues, and 21 Category 3 issues. Overall, through industry's efforts in addressing the Category 3 CANDU safety issues and the CNSC's effort in assessing submissions, there are now 25 Category 1 issues, 45 Category 2 issues, and 4 Category 3 issues. The recategorization process includes the following steps. A licensee will provide their submission stating the request for recategorization and include the supporting documentation addressing the path forward, the risk control measures. The CNSC staff then review the submission and evaluate the recategorization request based in view of the measures to be taken for the CANDU safety issue. After it has been verified that the risk control measures have been implemented, the Category 3 CANDU safety issue is recategorized to Category 1 or 2. The definitions just provided are used to determine if the CANDU safety issue is moved to Category 1 or Category 2. Okay. From 2007 through 2009, the CNSC applied its risk-informed decision-making process to review and document the status of the Category 3 CANDU safety issues, determine the risk significance of the Category 3 CANDU safety issue, and develop the path forward for the resolution. As mentioned, these are the risk control measures. Risk control measures could include changes to the design, modifying operational practices, and improvements to the knowledge base, for example, through carrying out experiments and research, or carrying out further, more detailed analyses. The risk assessment that was developed in a 2009 report was reviewed by CNSC management, questioned, challenged, and revised according to our management system processes. And then the CNSC staff engaged with industry to develop the risk control measures for resolution of the Category 3 CANDU safety issues. It is important to note that following the risk assessment, there were no items that required immediate attention by the licensees. The final report was published in 2009 and was made available to the public. We have presented this work in an International Atomic Energy Agency meeting on good practices in heavy water reactor operation, also to the CANDU senior regulators, and was also documented in the 2010 report to the Convention on Nuclear Safety. As discussed, through application of the risk-informed decision-making process, there are 4 remaining Category 3 CANDU safety issues. I will now turn the presentation over to Dr. David Newland.
Good afternoon, Mr. President, members of the Commission. My name is David Newland, and I am the Director General of the Directorate of Assessment and Analysis. First, I would like to note that the industry has made significant progress in implementing the risk control measures for the CANDU safety issues, thereby enhancing the safety of CANDU reactors. The remaining 4 Category 3 CANDU safety issues are related to need for systematic assessment of high-energy line break effects, analysis for void reactivity coefficient, fuel behavior in high-temperature transients, and lastly, fuel behavior in power pulse transients. The regulatory positions and paths forward for addressing these Category 3 issues are well established. Further experimental work and analysis are required to confirm the acceptance criteria and analysis methodologies proposed for use in licensing applications. We will discuss the status of each of these 4 Category 3 issues in more detail in the upcoming slides. High-energy pipes are those containing fluids at high pressure or temperature. In the event of a break of one of these pipes, there is an energy release which could lead to safety systems, equipment, structures, or components being damaged. For the primary side, Darlington Nuclear Power Plant was the first CANDU station that explicitly addressed the requirements for protecting systems, structures, and components from the effects of postulated primary heat transport pipe rupture, based upon industry best practices at the time that the station was designed. The design of the Darlington station has adequately protected the systems, structures, and components from the consequences associated with a postulated rupture of high-energy piping by constructing isolation barriers and engineered restraints against jet impingement and pipe whip, or through leak before break assessments being performed. An assessment was also performed for the Bruce B station at the design stage. However, for other nuclear power plants in Canada, the issue of high-energy line breaks on the primary side was not fully addressed during the design stage. The layout of plant equipment applied the defense in-depth philosophy and implemented physical separation of special safety systems and separation between high-energy systems and special safety systems. However, not all energy lines and locations were analyzed at that time. On the secondary side, all CANDU nuclear power plants have constructed isolation barriers, engineered restraints, or performed leak before break assessments to confirm that the impacts from high energy line breaks are acceptable. So for the path forward, licensees must complete a systematic review of high-energy piping breaks inside containment, assess the consequential damage associated with the postulated failure, and identify potential design improvements if necessary. Interim measures are in place, including appropriate periodic inspection and maintenance activities to support fitness for service of high-energy pipes. Moving to the current status, Bruce Power and OPG Darlington have submitted documentation to address the risk control measures sufficient to have this issue recategorized as a Category 2 issue. Bruce Power and OPG Darlington are expected to carry out further analyses to confirm and, if necessary, update their initial assessments, taking into consideration modern analysis approaches, operating experience, and the potential effects of plant aging. The methodology for systematic assessment of high-energy line break effects have been completed for Pickering A, Pickering B, and Pointler Pro. OPG provided the assessment report for Pickering Units 5 through 8 for CNSE review in July 2016. The assessment report for Pickering Units 1 and 4 is expected to be submitted to the CNSE for review by the end of 2016. For Pointler Pro, a comprehensive assessment is being performed for all relevant pipes in the reactor building. It is expected that the systematic assessment will identify and address any potential residual issues. The final assessment report is expected to be submitted in September 2016, and this issue is expected to be reclassified to Category 2 by the end of 2016. Recategorization will be based on the outcome of CNSE review of licensees' research outcomes. Large break LOCA loss of coolant accidents, LB LOCA, is a category of accidents within the design basis for CANDU reactors. This category of accidents includes the postulated break of any large pipe or header in the primary heat transport system. Computer code simulations of large break LOCA accidents are performed to demonstrate that the performance of the safety systems is adequate and that the consequences of the accident are acceptable. In particular, the simulations must demonstrate that the shutdown systems are effective in shutting down the reactor and that the emergency core cooling systems keep the fuel temperatures below acceptable criteria. In the original identification of issues, 5 interconnected issues were identified for large break LOCAs. These issues are related to the adequacy of the knowledge base needed to support safety margins for these accidents. These were uncertainties associated with the void reactivity coefficient, behavior of the fuel during power pulse transients, behavior of the fuel in high temperature transients, rate of coolant voiding, and finally, moderator temperature predictions. For the latter two, the experimental knowledge base has been expanded over recent years so that these two issues could be recategorized to Category 2. This represents good progress in addressing the issues pertaining to large break loss of coolant accidents. We will now describe each of the 3 remaining Category 3 issues. Before describing each of the issues, it is worth spending a little time outlining the sequence of events during a large break loss of coolant accident. When the postulated break of the primary heat transport system occurs, the coolant pressure rapidly drops and the coolant boils, turning to steam. This is referred to as voiding. Because of the positive void reactivity coefficient, this increase in voiding results in an increase in power. This so-called power pulse is terminated very quickly, within a few seconds, by the automatic action of the 2 shutdown systems. As more coolant flows out of the heat transport system and the pressure drops further, the fuel heats up, and this is subsequently cooled by the action of the automated emergency core cooling system. Over the longer term, the emergency core cooling system keeps the fuel cool until the event can be finally terminated. With respect to analysis for void reactivity coefficient, The characteristics of the power pulse, size and duration, are based to a large degree on the void reactivity coefficient. It is important that the analyses use an appropriate value for this coefficient in the predictions of the power pulse and in the assessment of the adequacy of the shutdown systems. This parameter has been subject to multiple research and development findings, which have reduced the calculated safety margins for large break loss of coolant accidents. In addition, due to a limited number of experimental data, there is uncertainty with respect to the true value of this parameter. Over the years, as these findings have come about, defense in depth and design and operational enhancements have been implemented to provide adequate safety margins. Such measures include operational constraints and power deratings. Regarding fuel behavior in power pulse transients, as previously described, during a large break loca, there is a rapid power increase, the power pulse, which results in energy being deposited into the fuel. The behavior of the fuel under such conditions is determined by a combination of experimental data and complex analytical models. There is a limited set of experimental data of CANDU fuel behavior under power pulse conditions, and therefore it is difficult to fully validate computer code predictions at these higher energies. As described previously, defense in depth and design and operational enhancements have been implemented to ensure that the safety margins are adequate, given this uncertainty in the experimental database. With regards to fuel behavior in high temperature transients, a large break loca results in a mismatch between the heat generation rate in the fuel and the heat removal by the coolant, such that the fuel temperature rises. If the fuel bundle temperature becomes excessive, fuel bundle deformation could occur. Such changes in bundle geometry need to be better understood. Once again, defense in depth and design and operational enhancements have been implemented to ensure that the safety margins are adequate, given this uncertainty in the experimental database. We will now turn our attention to the final risk control measures for these three Category 3 CANDU safety issues. A CNSC industry working group was convened with a mandate to better define the issues pertaining to large break loca and to identify effective risk control measures. The main conclusion of the working group is that a composite analytical approach is a combined solution that could address all three remaining issues related to these accidents. The composite analytical approach involves analytical refinements aimed at providing a more representative assessment of the consequences of this event, taking into account pipe breaks, reactor physics, and fuel behavior. With improved knowledge of uncertainties, improved methodologies, and the implementation of modern standards, this approach is expected to confirm the adequacy of existing design provisions and safety margins. Specifically, this approach will be demonstrating that the probability of a large break loss of coolant accident is very low, such that the appropriate analysis methodology could be used to assess the accident consequences, and demonstrating the adequacy of safety margins for large break loss of coolant accidents through the use of realistic assumptions for pipe failure probability and break opening times. Thirdly, ensuring that the assumptions, criteria, and data used in the analysis are well supported void coefficient of reactivity and reactor kinetic parameters, and a set of parameter limits which assure that the integrity of the fuel is maintained. And finally, demonstrating the effectiveness of the two shutdown systems and the emergency core cooling system through use of appropriate acceptance criteria in the analysis of these accidents. CNSC staff acknowledges the significant effort spent by the industry to complete the composite analytical approach and to consolidate the current state of knowledge in key areas. The pilot project demonstrated that this approach is a viable solution to realistically predict safety margins for large break loss of coolant accidents. Regarding reactor physics, the industry has made significant effort and progress in introducing more rigorous methods in the process of evaluation and estimation of uncertainties in CANDU reactor physics code predictions. The overall trend and progress is positive. However, further research and development and analysis is needed to address uncertainties and the scalability of the experimental data to representative CANDU conditions. Regarding fuel behavior, the industry has proposed a comprehensive framework as well as a systematic process for the identification of the barriers needed to be protected and their associated failure mechanisms. The derived acceptance criteria defined by the industry represent an improvement in comparison to the previous formulation and are better aligned with best international practice. Further work is needed regarding the technical basis for these criteria. The pilot analysis was an extensive industry effort, and CNSC staff note that there is consistent implementation of information from all technical areas considered. The industry has stated that a complete sensitivity analysis will be submitted with the planned regulatory submission using the composite analytical approach methodology. Details of the plans will be submitted by industry in 2017, and full regulatory submissions are expected in 2019. In summary, there is a clear path forward to closure, and we anticipate, subject to the regulatory review of submitted analyses, that all Category 3 issues will be recategorized in 2019. I will now turn the presentation back to Mr. Frappier.
Thank you. So as mentioned, there are 45 Category 2 CANDU safety issues that require ongoing regulatory oversight. The status of these issues is assessed as part of the CNSC's ongoing regulatory oversight in the appropriate safety and control area of safety analysis, design, or fitness for service. This includes ongoing reviews of component lifecycle management programs, supporting aging management and fitness for service, assessments of remaining confirmatory analyses that are ongoing, or verification of design modifications. These are tracked through the existing processes, and any significant development will be captured and communicated to the Commission in the annual regulatory oversight report that will be, as we're going to be doing tomorrow. Ongoing reviews to ensure that we stay up to date with any safety issue will be carried out through the periodic safety reviews that will become part of all licensees' license conditions. There were 3 interventions on this CMD, so we'd like to talk a little bit about what we heard on those. Overall, the interveners questioned the basis for the initial categorization and for recategorization of the CANDU safety issues. Detailed comments were provided regarding total loss of alternating current power, fire protection, fuel channels, hydrogen control, primary heat transport system relief capability, emergency core cooling strainers, and several others. CNSC staff emphasized that rigorous processes for the initial categorization and subsequent recategorizations were followed at all times. They were used for the initial categorization and for recategorization of the Category 3 safety issues. The basis of the initial categorization was documented in the CNSC report, Development of Regulatory Position on CANDU Safety Issues, Categorization of Safety Issues, which was published in 2007. For recategorization of CANDU safety issues, licensees provide their submissions stating their request for recategorization, including supporting documentation. CNSC staff then review the submission and evaluate the recategorization request based in view of the risk control measures that are going to be put in place for the CANDU safety issue. CNSC staff apply their in-depth science and engineering expertise in the assessment of licensees' submission. And independent technical panels have been called and will continue to be called in areas where established to support assessment of licensees' submission. So in conclusion, safety analysis and design have always been conservative, and all reactor types have ongoing research activities worldwide. Periodically, it is useful to review the information from research and operating experience and pull them together into the safety issues or safety areas for more consideration. We have consolidated the safety issues in the IEA Tech Doc on generic safety issues for nuclear power plants with pressurized heavy water reactors that Doug talked about earlier, with the CNSC's own generic action items that included findings from ongoing nuclear safety research and experience feedback from regulatory oversight or currently operating reactors in Canada and worldwide. Licensees must undertake focused actions on issues where further experiments and/or analysis are required to improve knowledge and understanding of the issue and to reconfirm the adequacy of safety margins. It is important to note that, as Dr. Miller mentioned, following the original risk assessments, there were no items that required immediate regulatory action by licensees, or by the CNSC or by licensees. Through application of the CNSC risk-informed decision-making process, the Category 3 CANDU safety issues have been addressed. The remaining 4 Category 3 CSIs are related to the systematic assessment of high-energy line break, the analysis for void reactivity coefficient, fuel behavior in high temperature, fuel behavior in power pulse transients. With the latter 3 grouped together as they relate to reactor behavior during large break loss of coolant accident, as previously discussed by Dr. Newland. The CNSC will continue to report on progress towards resolution of these Category 3 items. Currently, there are 45 Category 2 CSIs where licensees have appropriate control measures in place to address the issue and to maintain safety margins. The status of these issues is assessed as part of the CNSC's ongoing regulatory oversight of nuclear power plants. And going forward, we will identify and establish the path forward for safety concerns through the periodic safety review process carried out in accordance with the CNSC regulatory document on periodic safety reviews. And with that, our presentation is complete. We do have an example that is in the thing that we can go through if the Commission wants to. But at this point, we thought we'd stop and provide opportunity for any questions you might have.
Thank you.